Welcome to the Sophistic Online Documentation. In this video of the Composite Bridge tutorial, we show how to do the serviceability limit state design checks for the main girders of the composite bridge. Let's open the Composite Bridge design checks task that we created in the previous session to do the design checks in the ultimate limit state. We want to focus now on the checks for the stress limitation in the serviceability limit state. For this purpose, we also deselect the ultimate limit state checks. Note that the task keeps your settings and we can easily re-add the ultimate limit state checks later on. For the stress limitation in the serviceability limit state, we have two checks. Stress limitation in the characteristic combination and stress limitation in the quasi-permanent combination. Now we first will do the stress limitation in the characteristic combination. Let's go to the corresponding tab. You can see on the left we have the check for the stress limitation in the characteristic combination, and on the right the stress limitation in the quasi-permanent combination. Okay, stress limitation in the characteristic combination. What is it about? For the structural steel, we limit the von Mises stress to the yield strength of the material. For the concrete, we limit the concrete compression stress to K1 times FCK, where K1 is typically 0.6. And for the reinforcement, we limit the stress to K3 times the characteristic strength, and K3 is usually 0.8. The applied factors K1 and K3 are also depicted informatively in the tab. So now let's select the load cases for the check. In the list we have all load cases of the SLS characteristic combination. As for the ultimate limit state, I will select here the load cases superposed for max and min bending moment My and maximum and minimum shear force reset. As for the ultimate limit state, the results are stored on the load case number, calculated as number of the design load case plus the given offset. Please note that by default, the tension stiffening effect is considered in the stress calculations for the serviceability limit state. You can also switch it off, but here I would like to show you how it's taken into account. For this purpose, I will also add a detailed output at a section at the inner support for a load case superposed for minimum bending moment My, and set the output depth to show the individual steps of the stress calculation. Okay, let's run the task and take a look at the generated report. The structure is quite similar to the elastic design checks in the ultimate limit state that I have shown in the previous video. We have a table that shows for each section along the girder, for each material in the section, the calculated stresses, strength, the factors for the checks, and then the utilization, followed by an overview plot that sums up the decisive utilizations for each material type along the girder. Now let's take a look at the detailed stress calculation at the inner support. Here I would like to show you how the tension stiffening effect is considered. First, a short reminder what it is about. In a reinforced concrete slab acting in tension, the concrete in between the cracks still takes part in transmitting the forces in the slab. So even if the slab is cracked, it is stiffer than the pure reinforcements in the slab. Stiffness attracts loads, therefore the forces and reinforcement stresses in the slab of a composite girder are higher than those calculated using the pure cracked composite section, where only structural steel and reinforcement are considered as active. Since equilibrium has to be fulfilled, this effect leads also to a reduction of stresses in the structural steel part of the section. In accordance with Eurocode 4, Module Composite considers tension stiffening effect in the stress calculations for the serviceability limit state checks, but not for the ultimate limit state. When we go through the development of the stresses at the selected sections, you can see, just like for the ultimate limit state, how the stresses develop during the construction process and after adding the live loads. For the investigated MY load case, we have now a concrete slab acting in tension. As you can see, it is cracked, only the reinforcements are active in the slab. The primary effects from creep and shrinkage vanish in the cracked section, so stresses stay as they are. And finally, we have a step that applies the tension stiffening. As expected, the stresses in the reinforcements increase, while the stresses in the structural steel part are reduced. The magnitude of the tension stiffening effect depends on the strain in the slab, the mean tensile strength of the concrete, the reinforcement ratio in the slab, and the coefficient for the mean steel strain between the cracks. We also show these values informatively in the report. For further information how the tension stiffening effect is considered by the task, you can take a look at the manual of module composite, that is the engine behind the graphical task. Okay, now let's take a look at the second check for the stress limitation, the serviceability limit state. This check is about limiting the compression stress in the concrete to make sure that we do not have to care about nonlinear creep effects. The value for the stress limit depends on the national annex. Pure Eurocode recommends to limit the compression stress in the quasi-permanent combination to 45% of the characteristic concrete strength. Let's open the task and select the check. For the given structural system, I'm quite confident that the load case superposed for maximum bending moment My at the time of traffic opening is the decisive one. Let us select it. Run the task and take a look at the report. It is quite similar to the checks in the characteristic combination. However, here just the concrete stresses are checked. Okay, that's it about the stress limitations. Next point in the serviceability limit state checks is the limitation of the crack widths. For this topic, two checks are relevant. First, minimum reinforcement to avoid wide individual cracks in the crack formation stage. And second, the check control of cracking due to direct loading, which is about limiting the crack widths in the stabilized cracking stage. Okay, let's have first a look at the minimum reinforcement. When the concrete cracks, then the tension stresses in the concrete that are set free have to be carried by the reinforcement. Reinforcement amount in the slab should be sufficient to limit the occurring reinforcement stress to a value that guarantees the crack width limit. According to Eurocode 4, it can be calculated by the effective tensile strength of the concrete times the area of the tensile zone divided by the limit stress. That depends on the selected crack width limit and the reinforcement bar diameter, and also some additional factors. Let's do the check. The minimum reinforcement needs only to be placed in areas where under the characteristic combination tensile stresses occur in the concrete. So the load case selection for this check offers the design load cases superposed for the characteristic combination. In our case, the load case superposed for minimum bending moment My at the time with the most creep and shrinkage is of interest, because in our present bridge system, these will give the most tensile stresses in the concrete. Let's select it. Next, we specify the crack width limit. Note that we allow here 0.2, 0.3 and 0.4 mm as input, which are the typical values also provided in Table 7.1 of Eurocode 4. The input of an arbitrary crack width limit is not supported. By default, the task applies the maximum of the mean value of the tensile strength of the concrete, FCTM, and 3 Newton per square millimeter as effective tensile strength of the concrete. Note that you can also explicitly set the effective tensile strength of the concrete. I will also request a detailed output, for example, at x equals 13.6 meters. Okay, now let's run the task and take a look at the report. For the check, we provide an overview table along the sections of the design element. For each thin-walled concrete element, the necessary minimum reinforcement is calculated and compared to the existing reinforcement amount. Important point here that applies to all tasks and also to the stress calculation. Module Composite considers only the reinforcement defined in the cross-section editor, respectively Module Aqua. Reinforcements that might be defined or calculated with Module AQB are not taken into account. Note that where we have defined non-effective areas, the thin-walled elements are splitted and therefore listed twice in the table. Okay, next check. Drag control under direct loading. For a given reinforcement stress, the crack width limit can be either enforced by limiting the diameter or by limiting the bar spacing. Let's do the check. It is typically done for the frequent combination. So these are the superposition load cases that are offered for the selection. Once again, we select the load case superposed for minimum bending moment My at the end of life cycle, supposed to give the highest reinforcement stress. We once again select the crack width limit, request a detailed output at x equals 13.6 meters. This is where the reinforcement amount changes from the span to the support section. Run the task and take a look at the report. First, we get an overview table that sums up the limit diameter and the bar spacing for the given crack width, and then for every section along the design element, for each reinforcement element, in our case for the line reinforcements constituting the top-bottom reinforcement in the slab, the maximum reinforcement stresses. Note that we can compare this to the detailed output. Please remember that these stresses have per default been calculated considering the tension stiffening effect. And then we get a comparison of the limit diameter versus the actual diameter of the bars and the limit bar spacing versus the actually defined spacing. And if one of the two criteria is fulfilled, then the check is fulfilled. And as you can see here, this is the case for the whole girder. Okay, that's it about the serviceability limit state checks. In the next video, we will show how to calculate shear forces for the design of the shear connection between structural steel and concrete.